Okay, so this problem is asking us to find out a solution for this differential equation that was based on a beam. And a beam has a supports on the ends, and how it's going to, the bowing, I guess, is what we're interested in. And supports at the end make up your boundary value problems, or make up your boundary values. So I want to highlight our given information here, that we have y at 0, y prime at 0, and then we have y at the other end of this at L, and then y prime at L. And I also want to note that this is actually a fourth order differential equation. We have constants E, I, and W, and then we have the delta function. All right, so right now this is a function that lives in the real world in t, and we want to bring it to, or an x, I guess. This is an x value. And we want to bring it to the s world. So we're going to go from x to s, and we're going to do that with a transformation. I don't know if we want to get rid of this EI at this point. I think we might as well, since those are just constants. Let's bring this over to the other side. So let's start off with our problem. Let's see if we can start here. So this is the fourth derivative of y as a function of x is equal to w sub 0 divided by EI. And then we just have the delta function. And L is a constant, so the 1/2 L is constant. All right, in our transformation, when we transform this using Laplace, the Laplace transformation, we have to remember the Laplace transformation of derivatives. And this is a fourth derivative. So do you remember how it goes? I think it's s to the fourth.
Yes. And then,
Y of s, and then a bunch of minus.
and then f evaluated at 0, the y evaluated at 0, then minus s squared, y prime evaluated at 0, x to the first power, y evaluated at 0, and then there's minus y to the power.
I'll buy that. So this is the whole left-hand side. That's the derivative. I need more room, so I'm going to move it a little bit. And then the right-hand side is the constant. Now, those constants, remember, because this is a linear transformation, they just remain constant. So W divided by EI. And then now we need the transformation for the delta function.
Even instead of s and over to the
1/2 L times S. My S's. All right, are we good? Yeah, so the nice thing about this is that there's going to be a bunch of things that would disappear, so that's good. We can use this information, but we don't. So the issue is that we're going to have a little bit of a problem here, because This is not an initial value problem, so we don't have all the initial conditions for the double prime and triple prime. We have these highlighted ones. We know that this is equal to 0 from the initial condition, and then this is also equal to 0 from the other initial condition. But then we don't have this information, and so this is where the trick comes in. What we're going to do is we're going to set y double prime of 0 to be equal to C1, and then we're going to set y triple prime of 0 to be equal to C2. And what we'll do after we solve for the rest of this stuff is we're going to come back here and use the other two boundary conditions that we didn't use, and we'll plug that into our final solution with a C1 and C2 and hopefully be able to solve for C1 and C2. All right, so after all that disappears, we're going to have an s to the fourth, our unknown y of s function, 0, 0. We're going to have a minus C1 s minus C2 is equal to that constant times e to the minus as, and a in this case is 1/2 L. All right. So let's solve for this. Y of s is equal to all this stuff. Let's say C1 divided by s cubed minus C2 divided by s to the fourth, or plus, and then a plus W naught EI times e to the minus 1/2 L s divided by s to the fourth. Does that look okay? All right, now we need to bring it back to the real world, and we need to know some transformations and inverse transformations of things. So we need to know the transformation that brought us to s cubed, or s to the nth power. You guys remember those? L of something is equal to 1 over s to the n, or something, or something, or something. What? 1 over s to the n. Do we need our table? N factorial divided by s to the n plus 1. So n factorial divided by s to the n plus 1. What was that? T to the n. Or in this case, we need to go back to x, because technically that's our variable. But we'll deal with that later. That's of minor concern. And now, if we have an exponential, that gets brought back as something with a shift, right? And so what we need to do is we need to figure out what that shift is. So something with an f, s, e to the minus a, s What is that? One over, I need a t, what? F of t? I need more room. Actually, I think oh, we're going to come back. Yeah, we're going to use x. But, so, what was it again? What was that formula? That was something with a u, the Heaviside function, the shift. What was it? So f of t times u t minus a. Does it go like this? Does that f of t, or is that f of t minus a? Are you guys guessing, or are you looking it up? I was hoping that somebody would actually look it up, so I don't have to. So here it goes, right here. So there's a shift. So this is these are the two things that we want. These are the two transformations that we want to use to be able to pull back to the real world. So we need some adjusting, I think. The adjusting we need to do is with the constants, because we need an n factorial. Oh, this should be n plus 1, right? So we need an n factorial. So n is equal to 2 for this first one, so we need a 2 up on top. So we're going to force a 2 up there. And this one, n is equal to 3, so we need a 3 factorial on top and the bottom. So we get a 3 factorial over s to the 4th. Okay, so let's rewrite this so that it might look a little bit neater. So we got a constant c1 over 2, and we have a 2 over s cubed, and that's going to pull back to the real world as x to the second power. And then this one will have c2 over 6, or 3 factorial, and then 3 factorial over s to the 4th. We'll pull back as x to the 3rd, s to the 4th, I mean. We'll pull back as s to the 3rd, x to the 3rd. And then this w over ei and e to the minus 1/2 L s divided by s to the 4th. Oh, we need to do that too. So we need this fs over here needs to be something that we can pull back easily. And so this is to the 4th. So we need a 3 factorial again like we did before. So let me rearrange this. Sorry, I'm going to have to erase. And come back over here and say we actually wanted to multiply by 6 over 6 again. So the 6 in the denominator will just stay in the denominator. and then we have 3 factorial over s to the 4th, which will pull back as x to the 3rd, but with a shift because of this e to the minus 1/2 L times s. All right, I don't know if highlighting will work here, but these are the f functions that we need to pull back. All the others that are not highlighted are constants. And then we need to just be a little bit careful about pulling this last one back. All right, so let's pull it back and go into our real world. Y of x is equal to c1 over 2, and then this gets pulled back as t squared, or x squared, plus c2 over 6, and the 3 factorial over s squared gets pulled back as x to the 3rd, plus we have a constant w naught 6 ei in the denominator, and then now the pullback over here is a shift. So it's actually x to the 3rd power that's been shifted by 1/2 L times the shift function. X. Is that cool? So this is x minus 1/2 L. All right, wish we were done. But we need to solve for C1 and C2. So we have this information. We have y using the boundary, the other boundary. We have y of L is equal to 0. And what happens when we put L in for x? We're going to get C1. This is going to be L squared over 2. Plus C2, L squared over 6. L cubed over 6. Plus, see, we put L in here. L minus 1/2 L is 1/2 L, right? To the 3rd power. Oh, times all that stuff. So W naught 6 E I, and then now it's 1/2 L to the 3rd power, and then this shift over here, U 1/2 L. All right, and then we have y prime, so we need to take y prime, and that is going to be C1x plus C2 over 2 x squared Oh, do we not take the derivative of this? What's the derivative of this? I'll say the derivative is 0, but I don't know if that's correct. Okay. Derivative. I'm stuck. What do you think? Let's take a look at a graph and see if that'll help. Just to make things easy, let's assume that L is equal to 2 or something like that. So we got the U. I have that U thing. All right, our function, I just want to focus on, I even just want to take out the W naught 6EI and just focus on this. So let's say Y is equal to X, and then I said L is equal to 2, so I'll just do X minus 1 to the third power times the step function. X minus 1. So I'd like to say that that's 0. I don't know if that's enough of a proof that it's 0. But the derivative is 0 and the function itself is 0 at x is equal to 1. So let's see. L is 2. So 1/2, and let's use this. So this is L is equal to 2. I'm using N for L. L is equal to 2 in this case. And this is what happens at 1/2 of N. Right, but when you put in N, you're going to get 1/2 L. Does that make sense? Yeah, so what I'm trying to get at is there's probably a nicer way to explain this, but when you put in y prime evaluated at L, you're going to get a C1, and then x is equal to L plus C2 over 2 L squared plus all this other stuff that's going to turn to 0 after we put L in. Yeah, normally you would. Not necessarily, but I'm kind of relying on the graph in this case, because the graph is, yeah, because of the shift, the idea that there's a shift, when you put in that value, it's like putting in 0. So let's just say that this whole thing will equal to 0, and that this whole thing is also going to equal to 0. And I'll look this up again and see if I can have a better way to explain it. But the explanation here is by looking at the graph. So by the graph, all these things would disappear. So we're really just left with these two equations, and they're both equal to 0. So let's see. I'm solving for C1 and C2. So let me rewrite C1 L squared over 2 plus C2 L cubed over 6 is equal to 0. C1 L plus C2 L squared over 2 is also equal to 0. So this is really just a system of linear equations, two equations, two unknowns. And then we can solve for it any way we want. Is it easy enough to solve using a matrix, I wonder? Well, let's do one of those substitution things or whatever. So C1 from the second equation is going to equal to negative C2, and then divide by L, so this is L over 2. I guess if I plug that in, they're both going to be 0. Yeah, it can't be right now. Yeah. It doesn't? Oh, okay. All right, we still have hope here. Plug this back into the first equation. We're going to get negative C2 L over 2 plus C2. Yeah, it is going to be 0. L cubed over 6. Oh, is that going to help? So C1 is negative C2 L over 2 times L squared over 2. Yeah. That's not going to work. Because it looks like unless this thing is 0 here, which is what we're getting. I don't think that's 0. And then, so that's this first part, and then the second part is this business over here. Let's see if we got that one correct. So this is the coefficient of the step function, which looks like it's going to be W naught divided by 6 times E times I times X minus 1/2 L raised to the third power. And then this is 1/2 L. So right now we're getting 0, which is probably not correct, but I'm going to put 0 in here. It's not. Is the other stuff correct? Okay, so it's not 0, which means I probably made a mistake in setting these things equal to 0. What's this? The step function is X L L. All right, so I guess I'm going to have to look this up because I'm not remembering how to get this derivative and how to evaluate this function there. How about the other Dirac delta functions in this section? Is that okay? The other homework problems? What? Those are okay? So you guys can figure these ones out? The what?
Ask for extension.
Well, this one's due on the 7th, right? All right. Well, aside from the delta function, which is what we're supposed to talk about today, there was probably some other transformations that we should discuss. And so we're not going to do the convolution in 7.4, but there's this other piece of information in 7.4 that's kind of important that I wanted you guys to know about. Yeah, we skipped 7.4, but then I want to come back and talk a little bit about this particular transformation. So there's another transformation that takes a transformation that takes a t times another function, gets transformed into a derivative of whatever that function is. So let's see how this might work, or how this might be useful. So let's say what are some of the transformations that we know? e to the 5t. What's the e to the 5t transform to? So we know this transformation, right? That means, according to this this theorem, if we transform t times e to the 5t, what should this equal to? No, not, you can't break up the multiplication. So here you have to actually use this theorem. And so the transformation becomes, this is like n is equal to 1. That's the power of t. And so this is negative 1 to the first power. And then the first derivative, or dds, of this transformation, 1 over s minus 5. Well, they can just put this into the integral formula for the transformation, and then they'd come up with something like this. And so what is the derivative of 1 over s minus 5? Okay, so the negative and the negative would make that into a positive, so this is just 1 over s minus 5 squared. Right? Does that make sense? All right, let's try another one. Let's try the Laplace transform of t squared e to the 5t. According to this formula, n is equal to 2, so that gets transformed to negative 1 squared, so that's positive 1. And the second derivative of the transformation, that's already in s. So this is the first derivative. The second derivative will remain positive. Two over s minus 5 quantity cubed. Okay. All right, so if you have something that has a t or a power of t in front of it, and you're transforming that to go from the t world to the s world, then it's a matter of taking derivatives. Okay, questions? All right, let's see if we can do another problem. Do I have a problem? Let's do number 7. Yeah. This one? So my Fs is equal to s minus 5 to the negative 1 power. So the first derivative is negative s minus 5 to the negative 2 power. So the negative here and the negative here cancel each other out, becomes positive. But now if I want the second derivative, the negative and the negative here become positive, so this is 2 s minus 5 to the negative 3 power. So that 2 is up here, it stays positive, the negative 3 becomes s minus 5 to the third power in the bottom. So there's a 2 that comes out. And then if we try to do it again to the third power, then it should be 3 times 2, or 3 factorial coming out. Okay. Any other questions? All right, let's see. Let's do one more function, or one more differential equation here. This one I hope should be easy. Okay, so everything is set up. We have ready to take it to the S world by doing the Laplace transform, and we're going to get y double prime. So that would be s squared y of s minus s. Is it y or y prime? Y of 0 minus y prime of 0. Right? Okay. So this is one of those things that you after doing a bunch of problems several times, then this should be kind of almost automatic. And if it's not automatic yet, then I suggest going back and redoing some of those problems, because we're just doing a transform of derivatives. So see a lot of confused faces out there. And if you can ask questions, you should ask, but you should really just do your work. So the first derivative is sy, the capital Y of s, minus, and this is the first derivative, so that's just the original function. And this is both going to be multiplied by 2, and then this is equal to the delta function with a shift at 1. So e to the negative s, 1 times s. And we solve for capital Y. I'm going to see if I can underline them and put that together. So we have an s squared minus 2s and then the rest we can get from the initial conditions. We can replace them. So the y of 0 is 0 plus 2s. Yep. Okay. So the y of 0 is 0. The y prime of 0 is 1. So we got a minus 1 in here. This is 0. And then that's it. So we bring the 1 over to the other side. The negative 1 becomes a positive 1. Plus. And then we'll divide y of s is equal to, and it's usually beneficial to split this up into 2. And while I'm at it, I'm going to factor the denominator because this is going to be an exercise in partial fractions. And since both of these denominators, the numerators are 1 for both of these denominators, except for this e to the s. E to the s is a constant that I can just kind of move out. I really just need to decompose the partial fraction for 1 over s and s plus 2. So if you multiply by the common denominator, I don't know if you guys have seen this, a s plus 2 plus bs. This whole idea of a cover-up method where you cover, if you let s equal to 0 or something like that, you're going to find a value for a. Or do this any way you want. But this works as long as there's no multiplicity higher than 1. So let s equal 0, for example. We're going to get 1 is equal to 2a. And this is 0, so it goes away. And you get a is equal to 1/2. If you let s equal to negative 2, you're going to get 1 is equal to negative 2. So a is gone, so this is minus 2b, and then b is equal to negative 1/2. So your decomposition will look like this. It'll look like a is 1/2 times 1 over s, and then b is negative 1/2, 1 over s plus 2. And then the same thing is going to happen over here. All right, so we need to transform this back. What's a transform? How do you get this s 1 over s back? Is it 1 or t? T? I don't know, I'm asking you. It's 1? So that transforms back to 1. So y of t becomes 1/2 times 1 minus 1/2 times, what's 1 over s pulled back, or 1 over s plus 2? Okay. Now, there's a shift over here, so the 1/2 is constant. We'll leave that out. What's the shift here? This is 1 over s times e to the negative s. So it's a -1 shift, right? So that's a u t minus 1 that's shifted. And then this thing over here gets pulled back also. So the s, 1 over s plus 2 gets pulled back as e to the negative 2t. So this is e to the negative 2 times t, but the t is shifted with the Heaviside function, and the shift is by 1 again. So this is t minus 1.
So whenever it has like the Heaviside one, you have to check
According to this transformation, the f function in the real world gets shifted also with this thing. And I think that should be it. Okay, any questions? Yeah. So after I found A and B, this thing gets split up to A times 1 over S. So this is A times 1 over S, or A over S. I could put 1/2 on top of the S. And this is B with a negative sign over S plus 2. And then you're going to get the same thing over here, except you have e to the S hanging out. So you can just either pull that out as a constant, or not a constant, but pull that out as a factor, or I just split this up as A again and B, and then there's e to the S that we can't do anything about. That's going to be part of transformation. All right, any other questions? All right. So what's next? What's next is I was going to go into the next section, or next chapter. All right, so we have, just to recap what we did the Laplace transform stuff, 7.1, 7.2, 7.3. 7.4 we skipped, except I went over that just today. I went over the derivative of the transform. And then we did the delta function in 7.5. Okay? So we're not going to go over 7.6. It's because I wanted to save the systems of linear equations in Chapter 8. So in Chapter 8, we're going to go over 8.1 and 8.2. And then that would be it. We're out of time after that. So let's get started with 8.1. Where's 8.1? So 8.1 introduces us to a system of linear equations, or linear system of differential equations, a linear system of differential equations. That looks like this. So we're going to be dealing with matrices. And this is, I guess, kind of a little abstract right now, but if we take a look at, have you guys heard of the predator-prey business example? Wolf and rabbit? Let's do wolves and rabbits. And so sometimes a system can be described with differential equations, like how much the wolf and rabbit population changes over time. So what we could do is to kind of bring this into an application is that we can denote our W as a wolf population. We'll denote R as a rabbit population. And we can describe a system by finding out how the wolf and rabbit population changes. So we can, I'm just going to make this up, we could say the wolf population changes over time, and it changes over time depending on how much wolf population and how much rabbit population is currently there. So I don't know, I'm just going to make up some numbers at this point. Let's put a -3 and +5R. And then the rabbit population changes with respect to the amount of population for the wolves and the rabbits. So minus 2W minus 4R. So this thing can describe a system of populations between the wolves and the rabbits. And this is a linear system. In our case, the general system would have other functions that could be out here. And if we have other functions that are out here, then that would be non-homogeneous. But in this case, if there's no other functions aside from the wolf and the rabbit population, then it would be a homogeneous system. These functions over here, if all these f functions, I'll say f sub I of t is equal to 0, then the system is homogeneous. Really, we can kind of take a look at this system as if we bring everything over to the other side and set it equal to F1, F2, F3, etc., then we can see that it's non-zero, equal to non-zero. It's linear in the variable x1, x2, x3, and then you have these functions, which for our case, we're just going to be dealing with constants. And then this is going to be your function on the other side that would make it either homogeneous or non-homogeneous. So in this case, since our functions only depend on R and W, and there's no other functions like a sine or a cosine or t squared or anything else out here, we're going to assume that this is an example of something that's homogeneous. Okay? So the idea is to put this into matrix form, and we can write this into matrix form by looking at the coefficients of those functions. So this is what I mentioned earlier. If all the f functions were all equal to 0, then you have a homogeneous system. Otherwise, you have a system that generally looks like this. These are all the x's. This end up being your solution matrix or solution vector. I guess I could call it a matrix or a vector. Is equal to a times x plus f for some matrix of functions. And then the solution is going to be given by this vector. So in general, we're going to want to solve for a bunch of functions, and we can just compactly put those functions in vector form or matrix form. The book calls it a matrix. I guess I'm going to go back and forth between calling it a matrix or a vector, because I think it can be considered as either one. Okay? All right, so I think for now we can stop here. What we'll do next time is I'll find out the solution for that problem, figure out what the values are for those endpoints and its derivative, and then we'll continue on in Chapter 8.